RS latches with NAND gates and NOR gates. So the foundation of a 1-bit memory is based on the OR gate with feedback. As you can see in this figure 16.1 from my notebook, and you can see this is a 1-bit memory. It is made of one OR gate with a feedback. We have the output connected to the input, and there is a switch here which is always closed, and right there you can see that when in blue ink, when the first state, so when the input is 0, the output is 0, and the feedback goes here, so 0 plus 0 is equal to 0. Now when you enter 1 bit logic 1 here, 1 plus 0, the previous state, gives you a 1. Now the green 1 goes here, so we have 1 and 1, we stay there, and we have an output equal to 1. When you remove this bit to 0, the bit will stay there because 1 plus 0 is equal to 1, so it'll stay there. So that bit was transferred in green and was stored in red. Now the thing is, how do I erase that bit? Once it is stored, it is erased when you open the switch, because when you open the switch you will have a 0, so 0 plus 0 will be equal to 0. Because you don't want to have a mechanical switch in a real digital circuit, so we add an AND gate to control the feedback, and we will call it the reset input. So here, let me amplify this image a little bit. Here you can see that when you have a 1, it'll be transferred, okay, as long as the reset input is equal to 0. Because if you have a 0, you have a logic 1 right there. This is an inverter, so you have a 1 here, the gate is enabled, is acting as a closed switch, and it'll be working the same circuit as before. And once you store the logic 1 here, and it'll be stored because we can see that in green color, when you want to erase that bit, you just apply a logic 1 here on the reset input. The inverter will make it a 0, and that will create a 0, and then you will have the feedback. You will have the bit cleared, okay? So this is when you have 2 AND gates in crisscross connection, or OR gates in crisscross, you are creating a 1-bit memory, okay? Just 1-bit memory. So similar to the previous circuit, it is this one when you have NAND gate 1 and NAND gate 2. But if you flip this one, you flip it horizontally, you will see that NAND gate is simulating the other AND gate we were using to control the feedback, because this one goes to the input. So, and this is a truth table. When you have reset and set in the low logic, that's not allowed. This is why I'm placing 2 pull-up resistors to keep up the logic in logic 1s, right here, where there's no change. So you apply a logic high on the set, it'll be transferred to the Q. So you apply a 0 on the reset. When you press the switch, that 0 will be transferred to Q, to not Q. If you apply a 0 on the set, the set will be transferred to this Q, okay? So this truth table follows the circuit. You can, as an assignment to you, you can do this by applying colors and to show me that this truth table is working as it is expected with these inputs and outputs, okay? And you can make also the latch, set reset latch, with two NOR gates, but in this case the NOR gates work with positive logic. This is why we need two resistors, two pull down resistors, keeping the input logic low, where there will be no change. And you will never have the high logic on both sides because that's not allowed, and thanks to the pull down resistors. So if you apply, look at the table, you apply a logic high on the set, it'll be transferred to Q. So you press this switch, it'll be transferred to Q. Or you press this switch, it will transfer to not Q. So that way it is the way we have a latch or 1-bit memory. They are known as latch set resets. And another topic for this is a D-type flip-flop. The D-type flip-flop is the standard flip-flop that allows you to form registers. And registers are widely used in computer architectures and any type of microcontroller or microprocessor. A classical flip-flop is a 7474. I'm using here the HC, high-speed CMOS, where you have the clear and preset. They work with negative logic according to the truth table, and you have a clock. So a D-type flip-flop basically transfers the data input, the D input, to the Q output. For every clock pulse that you apply here, it'll be transferred. So if you connect the not Q to the D, it'll work as a toggle flip-flop, which means it'll be changing from state 0 to logic 1 according to the clock. So every time the clock enters, it'll change the logic. The truth table for this classic flip-flop is as follows. Let me reduce this so that we can see the truth table completely. Okay, so right here we can see it. We have the preset, which is called not preset, not clear, the clock input and the input, and two outputs, Q and not Q. The preset, what the truth table tells you is that when you apply, we don't care, X means don't care, so we don't care about the status of clock and the input. So if the preset is 0, the Q output will be 1, will be logic high, as long as clear is high. If preset is high and we apply a low pulse in the clear input, it'll be cleared. So the Q will be cleared, the not Q will be high. When I say clear, is logic 0. Now, when both inputs are in low logic, this is not allowed. That's why it has a note there. But anyway, you will see both inputs are logic high, which is not allowed. Now, when you have both inputs at high, there will be no change. So you have logic high and logic low, depending, because this is the original state you were having. And you have both inputs are logic high, right here, logic high, and the clock goes to the rising edge of the signal. The logic high in the D input will be transferred to Q. If you have a logic 0 on the D input and you apply a clock signal at the rising edge, this bit 0 will be transferred to the Q output. Okay, and so these two states are what we say they are synchronous, because they are synchronous with the clock. Right here they are asynchronous. So the preset and clear are asynchronous. That means they don't care about the clock, they change the state. But right here they depend on to transfer this bit to here and transfer this bit to here, to the Q output, they need a rising edge clock signal. Okay, and at the rising edge they are activated. And if you use CMOS 4000 family, the clock is activated at the falling edge of the signal. In the 74 family, it is activated at the rising edge. And when both preset and clear are high, and the clock goes from high to low, or it stays in low logic, it doesn't matter what state you have in D, the Q outputs will remain. So it'll store the previous data you were storing there. So Q0 means it stays in the previous state, and not Q, it stays there in the previous state. So the D type flip-flop, as I said, is the main device to have to form latches registers. So we will see latches and registers in the next lesson. Okay, and that's all for today.